of elements in the monster over a set of parameters capital A to denote the rank of the type of this tuple over A. A bar over capital A. Okay? So just to shorten the notation, we can talk about the rank of a tuple over a set of parameters, which always means the rank of the type, according to our definition. Okay. So now let me summarize some of the basic properties of this rank. So first of all, we can characterize it in terms of definable sets. Okay. So we have that rank Morley rank of a formula phi of x is greater or equal than alpha plus 1 if and only if there exists an infinite set of formulas phi I of x, where I is an omega, such that all of these formulas are pairwise contradictory. And such that phi implies, such that each of these formulas implies phi. Okay, so if you imagine a picture, we have the universe of our monster. Assume I'm given a set defined by phi, so this is phi of m. And one can check now that the rank of this set, the rank of phi of x, is at least alpha plus 1. If it's possible to find infinitely many disjoint sets inside your set, such that the rank of each of the sets, phi I, is at least alpha for all I in omega. Okay. So this is a very natural property to expect from any kind of dimension, right? If you have a set of a certain dimension, you shouldn't be able to cut it into infinitely many sets of the same dimension. Okay. So we have this characterization in terms of formulas. Next, so the rank of a set of formulas, phi of x, is given by the maximum of the Cantor-Bendixson ranks of P, where P is a type in the space of types over the monster model, and phi is contained in P. Okay. Next, 3. We have that the Morley rank of a set of formulas phi of x is given by the minimum of the ranks of all sets of formulas phi prime of x, where phi prime is a finite subset of phi. Okay, so it has this finiteness condition. It's determined by the ranks of its finite subsets. Let me also remark that it's important here that we are working in a saturated model. So when I say here that I can find infinitely many pairwise contradictory formulas, so in this lemma, formula means L of M, the monster model formula. Okay, and some of the statements that I'm making, they're using saturation of the underlying model. They're using the fact that the underlying model is saturated, so I can realize types over small sets. I would need that in order to do it. So if I was working with an arbitrary model M, some of the statements wouldn't be correct. For example, 1 wouldn't be correct. Okay, now 4. Okay, let's see. No, let me add a bit more to 3. So if it happens that the rank of a set of formulas phi is less than infinity, then the degree of phi is the minimum of the degrees of the formulas phi, where little phi is a finite conjunction of formulas in the set capital phi. Okay, and such that the rank of little phi is equal to the rank of the capital phi. Okay, so again, it's just elaborating on this finiteness principle. Now, what are the formulas of rank 0? So a formula phi of x has rank 0 if and only if phi of x is algebraic. Okay, so it's instructive to use, well, yeah. Okay, so we have algebraicity characterized by rank 0. Next, if you take a disjunction of two formulas, so let's say I'm given two formulas, phi of x and psi of x, and I look at the disjunction, then the rank of this disjunction is just the maximum of the ranks of each of these two formulas separately. Okay, so it's given by the maximum of the rank of phi and the rank of psi. Okay. Next property, 6. For any set phi of x of formulas over A, there is a complete type P of x in the space of types in the corresponding variable x over a set of parameters A. So let's say this capital phi was a set of LA formulas. Okay, and then I look at okay, so I look at a set of LA formulas, then I can find a complete type over the same set of parameters such that the rank of this set of formulas is the same as the rank of the type. Okay, so it shows that I can always find a generic type in my set. So given a definable set or a type definable set defined by some collection of formulas, it's always possible to find a complete type inside this set, which has the same rank as the set itself. So it means that this type doesn't contain any more information in a sense of, well, in a sense of the rank than the initial set did. Okay. Okay, 7. If we have that the rank Morley of phi is equal to alpha, then the degree of this formula is the greatest natural number k such that we can find pairwise contradictory formulas Okay, we can find pairwise contradictory formulas, phi 1 up to phi k, which all subdivide the set phi. So we have phi I of x implies phi of x, and the ranks of these formulas are at least alpha. Okay, so and the ranks of phi I are greater or equal than alpha. Okay, so it's just so we try to drop the rank by cutting our set into disjoint pieces of the same rank, right? And since we assume that the rank is alpha, it cannot drop under this procedure. So it means that we must get stuck after after we have managed to find finitely many formulas like this. And that's exactly the degree of the type. Okay, 8. Adding algebraic information doesn't affect the rank. Namely, suppose that we have a set A, a subset of the monster. We have a tuple A, element B, and we have that B is in the algebraic closure of A, capital A, together with the tuple A bar. Okay? So assume B is algebraic over the data. Then, if we look at the rank of the tuple A concatenated with B over the set of parameters A, then it is the same as the rank of the tuple A itself. Okay? So what this property tells you that if you add some algebraic stuff to A, so if you extend this tuple by adding some algebraic, more algebraic elements, it doesn't affect the rank. Okay? And finally we have 9. Assume that I have a set X, a subset of M to the N, and Y, a subset of M to some natural number M, two definable sets. And assume that there is a map F from X to Y, which is also definable. Okay, assume it is a definable function. Such that all of the fibers have the same fixed dimension, have the same fixed rank, let's say K. Okay? So all fibers of F have the same rank, let's say equal to K. So for all A in Y. Okay? Then we can calculate the rank of the set Y from this information. Namely, Y, the rank of Y is equal, the rank of X is equal to the rank of Y plus K. Okay? So this is a very natural statement to expect, right? If at each fiber, the corresponding fiber has dimension K, then the dimension of the set itself should be given by the dimension of the set Y plus this dimension that each fiber adds. Okay? In particular, if we have a definable bijection, then it preserves the rank. And in fact, we don't even need a bijection. It's enough to have a finite to one map. So in particular, definable finite to one maps preserve the rank. Okay, so this is this list of properties is the minimum you want to expect from a notion of dimension or rank. Okay, so all these properties hold for more or less rank. I won't prove this, so I leave the proof as an exercise. All of these things are not hard to check. You just have to unwind the definitions and see what happens. Okay. So this summarizes some of the crucial properties of the rank. Now, we have the following lemma. If T is a countable theory, then T is omega stable if and only if T is totally transcendental. Okay, so omega stability, which we have defined previously, which is just means a few types over, well, the number of types over any countable set is countable. In the case of a countable theory, it corresponds to being totally transcendental, meaning that the counter-Bennigsen rank of any point in my space of types is ordinal valued. Okay. So I think you can, because of this discussion, you can already imagine how a proof would go. So this is also an exercise. So the idea, of course, is that if you look at now at characterization of Morley's rank, if it's not ordinal valued, then you can keep cutting your definable sets. You can start with some set, then inductively you cut on each step your set into infinitely many more definable sets, etc., etc. And this way you're going to build a tree using which you can show failure of omega stability. Right? So, and the other direction is also not complicated. So we have this equivalence, okay? So it means that in an omega stable theory, every type has an ordinal valued rank. So every type can be assigned a rank. So the level of generality where this rank works well is omega stable theories. So I want to restrict to omega stable theories now. So from now on, T is an omega stable theory. Okay, and let me remark also what happens in the strongly minimal case, which we started with. Question?
When you started writing the lemma, you said some of the items in the lemma depend on the saturation of the model.
Right.
So I believe that this should involve any model. So
wait, which one? This equivalence, you mean? Yes. Oh, right, okay. But look, because the point is that these properties, both properties here, they're properties of a theory. So you can, so in order to detect these properties, you can always work in a saturated model, in fact. Yeah. Okay. So now what we would like to do, we would like to define some notion of free extensions of types. Okay, so imagine the following picture. So we are in the monster model, and we have some set of parameters A. Okay, and assume that I have a type P of X, which is a type over this set of parameters. Let's say one type. Okay. Now assume I'm given a bigger set of parameters B containing A. Okay. Then, of course, by Zorn's lemma, by the Boolean prime ideal theorem, so you need a bit less than choice, you can always extend this type P of X to some type over B. Okay? So it's always possible to find some type Q of X extending P where Q is a type over the set of parameters B. Right? Well, there's a stupid way to do it. You can just take a realization of P, any realization of P you want, and look at the type of this realization over B, right? But the problem is that not all extensions of your type are equal. So some are nicer than the others. And what we want to understand now is how to extend the type from a small set of parameters to a larger set of parameters in such a manner that you don't add any new information, or that you add as few conditions as possible. Okay? Because what is a type? So type is like an imaginary element, which and the type tells you certain conditions, certain first-order conditions that it satisfies relatively to the parameters in A, right? So now I would like to extend it to B in such a way that I let as few new conditions as possible. So of course I will already have all the conditions imposed by A, but I want to add as few new restrictions on how my type can look like as possible. So I want to do it in a generic way. Okay? So this is the aim. And we will make it precise. So aim find a generic extension of P to this larger set of parameters B. Okay. There are various ways to do it. Most of these ways turn out to be equivalent, especially in the context of omega stable theories. So let me start with the notion of a definable type. Okay, definition. Turns out, in fact, that in an omega stable case, this extension, it's possible to perform it in a quite explicit manner. So for this, we will use the notion of a definable type. So let P be a type over a set of parameters A. Assume that we will say that this type is definable over a set of parameters B if for every formula phi of xy in L, we can find some other formula which is denoted as D subscript P phi of y, and this formula is allowed to use parameters from B such that the formula phi of xa is in P if and only if A satisfies the corresponding definition. So we have that dp phi of A holds. And we want this to happen for all elements in the set of parameters A, in the domain of the type. Okay? So once again, what is a type? So once I fix a formula phi, some of its instances are in my type, some are not, right? So then what I want to be able to do, I want to be able to define the set of those parameters for which phi with the corresponding parameter is in the type. And that's exactly what this definition captures. So it tells you that your type is definable when it's possible. For every formula in your type, you can define its parameters. Restricting to this set of parameters capital A, for which the corresponding instance of your formula is in the type. Okay? And it turns out that it's always possible to do in an omega stable theory, or even more generally in a stable theory. So theorem. Assume that we have M, a model, and assume we have a type P over this model. Then P is definable. Okay. And if I don't specify the set of parameters, I mean it's definable over its own domain. So definable over M. Okay. So note that it's certainly not possible that all types and all theories are definable, even purely for cardinality reasons. Because here, in this case, if I look at all types over M, if all of them are definable, then for each of them, I can pick a corresponding definition schema, right? And moreover, if I have two types, which both have the same exact definition schema, which define them, then these types have to be equal. But the number of choices for this dp phi, when phi varies over all formulas in L, is bounded by the cardinality of the language. Okay, so this shows that if all types over M are definable, then the number of types over M is small. That it's at most M to the power cardinality of the language. Okay. Yeah, but this is a condition which we know already holds in omega stable theories, for example, right? We know that there are few types in omega stable theories. So this result, it can be viewed as a refinement of the fact that there are few types. So not only there are few, but in fact they're definable, and we will construct explicitly this, such definitions. Okay. So let's prove this. In fact, I will work in a slightly more general setting than omega stability, so the result holds in any stable theory. Now, what is a stable theory? Maybe you remember, we had an exercise. So recall, we say that the formula phi of xy is stable which means that in no model M of t, we can find an infinite sequence of tuples ai bi such that I is an omega, such that phi of ai bj holds if and only if I is less or equal than j. Right? So this was our definition, and we had an exercise which says that in an omega stable theory, all formulas are stable. So recall, T omega stable implies that all formulas are stable. Okay? And now this is the condition. So to prove the theorem, in fact, we will only use this assumption that all formulas are stable. So we'll only use stability of the theory. Okay? So now, and also it's important, so notice here, we quantify overall models, right? So then, if I call it star, this condition star, so by compactness, star implies that in fact there is a finite bound. So it implies that exists some number n, which depends only on the formula phi itself, such that we cannot find such a sequence of lengths bigger than n. Okay. So there's a bound on the maximal possible size of this ladder configuration. Okay. So now I would like to prove this this criterion. We will work formula by formula. So it's a local argument. So more precisely, we have the following statement. So let delta of xy be a stable formula in the sense of this definition. Okay, so we have a model M as in the statement of the theorem, and assume we are given a tuple A in the monster model of the lengths corresponding to the variable x. Okay. Then there's a finite set of tuples aij such that ij are less than capital N of tuples contained in this small model M such that for any b a parameter in the model, we have that that delta of AB holds if and only if the following formula holds. So we have a Boolean combination of instances of delta. So we take disjunction over J, conjunction over I, delta of Aij B. Okay, so what's the gain here? So note, the gain is that this parameter A, it comes from outside of M, right? So let me draw maybe an illustration. So I'm given my monster model M. Inside it, I have a small model M. And I have some tuple, little a. And I'm trying to understand the set, the subset of M that is cut out by the formula delta of AY. Right? So I have my formula delta of AY, and I look at those solutions of this formula that are in M. Okay? This defines me some subset of M. The subset of M a priori need not be definable using parameters from within M. Right? A priori there's no reason for it. Okay, it happens to be an intersection of a definable set with some submodel. But what we will show now is that in fact then this intersection is itself a set definable in M using parameters from M. And moreover, the formula that one needs to define the set within M is built out as a simple Boolean combination of instances of my formula delta that I start with. So it's a completely local argument. It's almost a graph theoretic statement. Okay? So the reason here is that all these new parameters that I find, all this Aij, they're all from my small model M. Okay. This property that every externally definable set, so you call such a set externally definable because it's an intersection of definable set with parameters outside with some smaller model. So the set that in a stable theory, every externally definable set is already internally definable in M. Okay, so it's a crucial property. It's a characterization of stability also, if you want. Okay, so now let's prove this combinatorial lemma about delta. So we have two steps. So first, let us take N1 to be as given by this statement here. So let me call this statement double star. Okay. So double star tells us that for every stable formula, there is a bound. There's a number n which bounds the maximal possible size of this sequence, right? AI, BI with those conditions. So let N1 be given by this condition double star for delta, assuming delta is stable. Okay? Claim for any formula psi of x in the type of A over M okay, so for every such formula, we can find tuples A1 up to AN in the model M, so in the small model now, such that all of them satisfy this formula psi, and little n is bounded from above by the capital N1, such that for any B in M, if M satisfies the conjunction over all I from 1 to n of delta AIB, then delta of AB holds. Okay, so we can force this implication by a conjunction of formulas inside them. Well, let's check it. Yes.
What is psi?
Let's see, what is psi? Psi is any formula in the type of A over M. Right, so not only I can find such tuples which force this implication, but I can choose them to look like A relatively to M at any finitary level. Okay, okay, let's prove this claim. It's a claim. Proof. So let's start building such a sequence. So pick elements A1, A2, etc. in M, satisfying this formula psi, and some elements B1, B2, etc. in M, such that not delta of ABI holds. Okay? And such that delta of AIBJ holds if and only if I is less or equal than J. Okay? So I try to choose as many elements with this condition as possible. So I keep adding them for as long as I can. Okay? So assume we have already found such elements up to some n. Okay? So we have A1 up to AN and B1 up to Bn, which satisfy this condition. Okay? But then we can look at the formula psi of x together with the conjunction over all I of the negation of delta of xbi. Okay, so now what can we say about this formula? This is a formula over M, so all parameters are in M. Okay, it holds on A. Okay, it holds on the initial tuple. Hence, it can be realized in M by some element AN plus 1. Okay. Well, why this is the case? I mean, it's always true, right? Whenever you have a formula with parameters from a model, from an elementary substructure, which is satisfied by some element in a bigger model, because it's an elementary substructure, there's an element already in the small model which satisfies the same formula. So this is the step which really uses that M is a submodel, not an arbitrary set. Okay? So we can realize it by some element AN plus 1 in M. Okay, but now we have that either A1 up to AN plus 1 satisfies the claim or there is B in M such that the conjunction, but now up to N plus 1, delta of AIB holds, but not delta of AB holds. Okay? Now this new element, B, so we can take Bn plus 1 in M to be this B. Okay, so we take Bn plus 1 to be an element B with this property. Okay. So the construction can be continued. Okay. And the point is that you cannot continue forever because this requirement that delta of AI Bj holds if and only if I is less or equal than J, we know that this is forbidden. We can only do it for finitely many steps, right? So this means that at some moment you must stop, in which case you get stuck and you cannot find such a B anymore, which means that you have achieved what we have achieved what we wanted. So we have found this A1 up to AN plus 1 satisfying the claim. So this must stop. after capital N1 steps. And then the step on which we got stuck gives us the right formula. Okay? So this proves the claim. Okay? Now we pass to step 2 of the construction. So we want to get the implication in the opposite direction. For this, let's consider the formula xi. Okay, so this is proof of the claim. Now let's consider xi, a formula in the variables x1 up to x and 1, y. Let this be the formula delta of x1, y, and delta of xy, 2y, etc., and delta of x and 1, y. Okay, so I take a large conjunction of the instances of delta, where the size of this conjunction is bounded by n1. So something which depended only on the initial formula delta. Okay. Now, note, so this is something that, okay, I suggest to check as an exercise, is that any Boolean combination of stable formulas is again a stable formula. Okay. So any Boolean stability is preserved under Boolean combinations. Now the point is that then this new formula is also stable with this given separation of variables into two groups. Okay. So we have that xi of x bar y is also stable because delta was stable. So we can it's easy to check that xi is stable as well. Okay, so let N2 then be given by the bound on the maximal size of a ladder for xi. Okay, so there must be a bound by stability. In fact, this bound can be calculated in terms of the bound on delta. I mean, it's a small bound. It's not Ramsey theoretic or anything. Okay. So we have N2 which works for xi, okay? And now we want to do something similar. Okay, so this formula which works for xi and also for the negation of xi. In fact, it's the same number, but never mind. So let me be explicit, okay? So like I said, Boolean combinations of stable relations are stable. So in particular, negation of xi is stable as well. So let N2 be a bound which works for both xi and the negation of xi. Okay, and now we construct, again, we try to construct a ladder contradicting stability. So we construct tuples A1, A bar 2, etc., all in M, which satisfy the claim above. So they satisfy the claim. And we also choose B1, B2, etc. in M such that the following conditions are satisfied. So first, we have that xi of A bar I Bj holds if and only if I is strictly larger than j. And let's see, and 2, we have the delta of A bi holds for all I. Okay, so we try to construct a sequence of A's and B's satisfying these two conditions. Okay, so suppose we already managed up to n. So suppose we found a bar I and bi for I from 1 to n. Okay, now by the claim, we know that there is some tuple an plus 1 in M such that psi of an plus 1 bi holds for I from 1 to n, and such that for any b, an element in M, if we have psi of an plus 1 b, then delta holds as well. So delta of AB holds. Okay? So if I look at the disjunction now, so I look at the disjunction over all I from 1 to n plus 1 of psi of ai y. Okay, let's look at the disjunction of all these instances of psi. So now if this disjunction doesn't satisfy the requirements of the lemma, okay, then we can find some element bn plus 1 in M such that delta of A bn plus 1 holds, but not psi of A bar I bn plus 1 for I from 1 to n plus 1. Okay? So if that disjunction doesn't work, we can continue the construction. We can keep going. And then we can keep going and going and going until we hit n2. And this is where we must stop, right? Because then we would have a ladder of size n2 which contradicts stability of psi, which contradicts the choice of n2. Okay, so this must stop. At some number n bounded by n2, and hence this proves the existence of the desired formula. Okay, so this gives us a formula. So the formula will be of this form: a disjunction of xi's, where remember each xi is a conjunction of instances of delta. Okay, so this proves the theorem. We have managed to define the same set that delta defined using parameters from outside of M, using parameters only from inside of M. Okay? Yeah, it's a bit combinatorial, but this is a remarkably important lemma. So it's the core of a lot of ideas in stability. So the definability of types is a very important property. If you see it for the first time, it looks like a bit random, but I hope to convince you later on while developing the theory that it's actually an important, very important condition. Okay? So now the point is that using these definable types, we can finally figure out how a generic extension of a type should look like. Okay? So for this, we define the notion of forking. Yes, of course.
So clearly you want something from here. So what is it exactly? Is that the formula is stable?
So the only thing, so this lemma is really a finite combinatorics essentially. So all I want is that the formula is stable.
Okay, so the assumption is for every stable formula in a bigger model.
Yes.
If it defines something in smaller.
Right.
In elementary or something like that, required in bigger models.
Right, exactly, yeah. You don't need anything about saturation in this lemma. It's really a finitary combinatorial, yeah. So all you need is that the set you cut out is in a model. So we used the fact that the smaller set was a model once. But you don't assume anything about the bigger model. Yeah, yeah, exactly. Okay, so forking. And as it happens a lot with Sherlock naming things, it's, of course, the positive property is going to be the negation of forking. It's going to be non-forking. Okay, so definition. Suppose we have two sets. So I'm in the same context, I remind you. I have my saturated model M realizing T. So suppose that A is a subset of B, P is a type over A, and Q is a type over B, extending P. Okay? We will say that Q is a non-forking extension of P if they have the same Morley rank. Okay, so I would like to argue that not dropping the rank, so not adding any new formulas which force you to drop the rank of your type, corresponds in this context to not adding any new information, to obtaining a generic extension. Okay, this is the definition. Okay, now we have a number of results about this definition. Let me begin with the following theorem. Let me check the time. Okay. Okay, so let's begin with some observations about this notion. So suppose we have a type P, a type over a set of parameters A, and so again A is a subset of B. Okay. So first of all, we want to argue that in fact you can find an unforking extension to any larger set of parameters. Okay, so 1 exists Q, a type over B, a non-forking extension of P. This is 1. 2, the rightmost degree of M, the degree, the Morley degree of P many non-forking extensions of P to B okay, and moreover, if we look at B given by the monster, then there are exactly the degree of P many extensions. Okay. 3, let me say that there's at most one non-forking extension. Wait, sorry. Yeah, okay, no, doesn't matter. Sorry. So in particular, if the degree of P was 1, we have a unique extension, right? Okay, and 3, assume I'm given a type over a model. So assume P belongs to the space of types over M, where M is an elementary submodel. Then an extension Q to some bigger set of parameters is non-forking, if and only if the type Q is definable over this small model. Okay, so Q has a bigger domain, B, which contains M. In particular, it could be all of the monster model. So in this case, we see this equivalence of these two notions. So when the domain of the type you start with is a model, we can show that in fact this non-forking, first of all, there's only one non-forking extension, right? Because okay, why? Why? Because moreover, we have that the defining schema for Q is exactly the same one that we had for P. So moreover, we have that that for any formula phi of x, y, and l, and for any parameter b, little b in the capital B, we have that phi of xb is in the type Q if and only if the defining schema that we have for P holds on B. So dp phi of B holds. Okay, and this happens for all parameters B. Okay, so basically this is some basic statements about existence and existence of non-forking extensions and uniqueness in the case the underlying set of parameters is a model. Next time we'll see that in fact one can be more careful and you can obtain almost uniqueness over any set of parameters. But in fact you don't really need a model here. We will show that all you need is an algebraically closed set. An algebraically closed set in the sense of MEQ. Okay, that is sufficient condition for this uniqueness of non-forking extensions for stationarity. But for now, let's just stick with this statement. Okay. I don't think I'm going to prove it. I think I have time for this. But again, this is completely standard fact. In fact, I have notes from some previous class I've taught. So I'll put a link, you can see the details, okay? Okay, I'll add the reference. So the point, okay, so what we have is that such extensions always exist. In fact, all of these results are much more general. So it's not, you can certainly investigate these things in omega stable theories, which is our level of generality. But in reality, it's much more general. So all of this can be done. Well, so 1 and 2 are in fact, okay, no. So 1 holds in any theory, in fact. There are no restrictions. Okay, not quite, sorry. So 1 holds in any what is called simple theory, for example. It's a much more general class of theories than omega stable. It holds over in any theory whenever this underlying set of parameters B is a model. Then it holds in any theory with no restriction. 2 and 3, they require stability. So this stationarity phenomena or bounded multiplicity phenomena, they're specific to stable theories. But in any case, so these are more general results. Okay. Yeah, so the proofs are not difficult, but now it's good to have some grip on this kind of extensions. Okay. Now we would like to use this notion of a free extension of a type to define a notion of independence on tuples in our structures. Okay. So now we talk about this symbol, anchor. Okay, so this is forking independence. Okay, so definition. For any small tuples of parameters, So for any small a, b, and a small set of parameters a, or capital A rather, we will write that A is independent from B over the set of parameters capital A if the type of A over the base capital A together with the tuple B does not fork over the underlying set of parameters A. Okay. When I say that the type doesn't fork over A, it's another way to say that this type is a non-forking extension of its restriction to a smaller set of parameters A. Okay. So i.e. a non-forking extension of the type of little a over capital A. All right, so we have this notion of, we have this definition. Now, turns out that this notion of independence, it looks a lot like the notion of algebraic independence that we had in strongly minimal theories. But now we work in a much larger context of omega stable theories. Okay? So it turns out that a lot of properties can be abstracted and carried out in this much more general setting. So we have fact properties of this independence. Let's restrict to omega stable theories. Although again, all you need is just stability. So you need that, it only requires stability of all the formulas. Okay? So this relation has the following properties. First of all is automorphism invariant. So if we have that A is independent from B over C, and we have some automorphism sigma, then the images are also in the same independence relation. So sigma of A is independent from sigma of B over sigma of C. Okay? So this is a condition which is easy to check from the definition. It's always formula by formula, right? Okay. Two, finite character. So assume that A is independent from B over C. Then this happens if and only if we have that A0 is independent from B0 over C for any finite subset A0 of A and B0 of B. Okay? The reason for this is again due to the fact that we have defined forking in terms of formulas. So type forks means that there is some formula in this bigger extension of your type whose Morley rank has dropped, right? But then it's enough to look at the parameters of this formula, and already with that smaller set of parameters, your type forks. Okay, so we have finite character. We have extension, which is basically just the theorem that I have just raised right here. So we have extension if I have A is independent from B over C, then for any set D, we can find an automorphism sigma which fixes CB. Okay, so this part remains fixed, such that sigma of A is independent from BD over C. Okay, so this is just the existence of non-forking extensions. of types. Okay. Now 4, so local character. If we are given a finite set of parameters, a finite tuple, if A is finite, and B is any set, then we can find a subset C of B, so exists C contained in B, such that the size of C is bounded by the cardinality of the theory, and such that A is independent from B over C. Okay, so whenever I have a set of parameters and an element, I can always find some subset of these parameters of bounded size, where the size is bounded by the size of the language, such that A is already independent from this whole big set over just this small set. So this shows somehow that that types have this local character. In 4, no. In 4, there are no assumptions. So that's the point. Every type doesn't fork over some small subset of its domain. This corresponds in the case, let's say, of an omega stable theory. This corresponds to the fact that you can always find a formula. So given a type, you can always find a formula which has a maximal Morley rank and degree, right? So you can once you are given like a type, you can already find a formula which essentially isolates it in the sense of rank. So in that case, you in an omega stable theory, you have even a stronger version of this. But the point is that all types are local. So no matter how large your type is, you can always find a small subset of the domain such that it already doesn't fork over it. Okay, so no other assumptions except for the stated ones. Okay, now next, this relation has transitivity. So whenever we have that A is independent from B over C, and A is independent from D over BC, then this holds if and only if A is independent from C over BD. Okay, so you can put things up. So you see, why this transitivity? Well, because you assume well, it's more visible in one of the directions. So you assume that you look at the type of A over this set of parameters, this whole set of parameters BCD. And now assume that you know that over restriction to B, the type of A over B doesn't fork over C. But also assume that the type of, okay, let me draw a picture. So we have A, this is BD, CBD. So I'm trying to understand the relation. And now I have my B, let's say, and then I have my D, okay? And what it says here that if I know independence of this set from this one and over the base C, and then I know independence of this set over the whole thing, but over this intermediate set B, then I can combine it to get independence from everything on the right side. Okay. So this is 5, transitivity. 6, symmetry. So this relation is symmetric. We have that A is independent from B over C, if and only if B is independent from A over C. Okay, so this is a symmetric relation. Okay, we're almost done with the properties. So the last one is stationarity. and again, this follows from the previous thing we have stated about non-forking extensions. So if we have A and B, and they have the same type over some model M, so okay, so if the type of A over M is equal to the type of B over M, where M is a model, then under the assumption that they don't fork with some extra set of parameters B, so if we have that both A is independent from B over M and B is independent from the capital B over M, then in fact the types of A and B are equal over this larger set of parameters. So then the type of A over Bm is equal to the type of B over Bm. Okay, so we have a bunch of properties which show, so to summarize, these properties make this relation look like a natural notion of independence. So for example, if you think again about strongly minimal theories, so if T is strongly minimal, then this notion of independence can be characterized simply in terms of the closure operator independence, ACL closure operator independence. So if T is strongly minimal, then we have the following observations. So first of all, we know that the Morley rank coincides with the dimension. Okay, so the Morley rank of any tuple A over a set of parameters capital A is equal to the dimension in the sense of the ACL that we have defined to the dimension of this tuple over A. Okay? And similarly, the notion of forking that we have just developed corresponds to the notion of algebraic independence in a strongly minimal structure. So A is independent from B over C if and only if A is not in the ACL of BC minus ACL of C. Okay? So you can check this characterization directly. Now the symmetry condition, so the symmetry property of this independence relation, it corresponds to the exchange, right? So then symmetry of the non-forking independence corresponds to the exchange of the algebraic closure. Okay? So in the case of strongly minimal theories, it coincides with the basic theory of dimension that we have developed. However, it's a much more general theory, and we have this new component, this coincidence with the definability of types, the coincidence of free extensions with definability. So this is a very important feature of forking and stable theories. Oh, okay. In fact, let me just say the last remark. In fact, existence of such a relation is a characteristic property of a stable theory. So it's an important result that assume you are given any theory, you don't know anything about it, okay? And assume you are given some ternary relation on small subsets of the monster model of your theory, which satisfies all these conditions. Then your theory is stable. So it's an if and only if. This gives you a complete characterization of stability without referring to formulas at all. It's just existence of a certain independence relation between small subsets in your structure. Okay. So this is an important condition. It tells you that you can develop some rudimentary notion of dimension and independence in any stable theory or in any omega stable theory. I guess that's what we really did. But you can do this in a stable theory as well. Okay. And next time we'll see how to use these ideas to analyze. To analyze models of uncountably categorical theories and other things. Yeah? Okay, thank you.